So, first things first, as always, I made updates today to the Module 3 notes. We're actually going to go through the demo file in Module 3 from the GitHub, not through the notes file. I explained this once before, but for those of you who walked in afterwards, tonight we're doing demo. The same sort of very complete, many examples, lots and lots of code sorts of notes are in the usual notes file. Tonight, because I want to go through slightly less and open it up for questions and actual practices, we're going to work from the demo file. So everybody wants to go to the GitHub page and just download the most updated Module 3, which will look like this. The other big thing I want to start with tonight is I want to thank everybody because your excellent questions is teaching me a whole lot about Python that I didn't realize. So I actually want to start just to rehash some our Python crosstalk that we had spoken a little bit about on Tuesday. So I know dplyr is one of the really cool, amazing packages that in R that people really love for very quickly assembling and aggregating and summarizing data sets. There is a whole lot more of that function in Python now because lots of people have gone out and have tried to actually basically make Python versions of dplyr. So I wanted to quickly point everybody to that. So where we left off on Tuesday, we spoke a little bit about this Jupyter Notebook magic, right? Which is what I showed you earlier. So before we loaded in this extension, we ran an R command through the cell, right? And here I'm using the -O flag to say that whatever variable is saved in this cell should be able to be exported out into the Python environment. So we ran the C command in R, and we were able to export the outputs of that command back into the Python environment. So that's one way to do it. But let's do some more fancy things. Yeah.
Sorry, I get an error with that.
That will not work for anybody who has not already loaded in the R Essentials, and the RPy2 libraries. So if we go
and you only ever have to do that once?
Only have to do it once. So that's in the instructions PowerPoint from before. The other thing is we did have a question from Tuesday about whether or not pandas can read in URLs, and the answer is yes, they absolutely can. So this is the URL to some of the data we'll be working with tonight, and you can see no problem. So you can just pass in a URL to a data set, or a URL that goes to a data set, pass it straight into pandas, and it will be able to read it in no problem. The other thing I wanted to cover real fast from pandas that I don't think I discussed on Tuesday is just very briefly, you can update the index. You can store one of your pre-existing columns, one of your pre-existing variables as the index and update the index, which might be really nice. Because for example, if, as we'll have tonight, you have a bunch of interestingly named Y variables, you can store that as your index, and you can very quickly just slice through by using the .log attribute and just by searching the string that you're looking for. Okay, so let's actually quickly go through some dplyr examples in Python. There are two main packages that are up and coming right now for that. First one is the dplython library. For anybody who wants to try it out, this won't work because we didn't previously install it. This is actually a really great example or time if you want to do a live in-person demo of how to install this. So we're going to need to run this command right here, this pip install dplython. So for anybody who's on a Mac, you want to open up the terminal. For anybody who's on a Windows, you want to open up the Anaconda command function. So if you go to start Anaconda 3 and the command prompt, and then all we should have to be able to do is pip install dplython. I've already installed it, so it's going to tell me that it's already met. Realize you can't see that now. Is everybody able to run that? Yep.
Could not find version satisfies required.
Ooh, okay, so we might have some dependency issues to go through. So, I know. Okay, we'll go through it. But a number of you were able to download it? Okay. So, if you run this cell, we're going to be importing from the dplython package a whole bunch of new functions that this guy wrote, which is wonderful. And with that, you can start using a whole bunch of dplyr-like syntax and doing all sorts of different nice aggregation and sifting things. So if you wanted to have dplyr in Python, this is one way to do it. So here we're using sif to separate out, and we're doing select to choose what columns we want to look at, and we're piping that onto head to look at the first 5 rows. We can do more complex things here using mutate, group by, and summarize. So we can make a new variable with mutate. We can do group by to aggregate, and we can do summarize to give us this nice little short table. So if you like dplyr, that's one way you can start doing it in Python now. That's one way you want to expand Pandas functionality. The other library is the Pandas ply library, which is also pretty new, and this one is a little less established than dplython, so there's probably more bugs in it, fair warning. But again, if you want to open up a terminal and run this pip install pandas ply, if you want this package, once you have it, you should be able to run something similar like this, which again has syntax more similar to dplyr in terms of very elegantly and efficiently working with data frames. So you can see we ran through it, and we can get all the cases where our XO1 variable was less than 5 and where our XO2 variable was greater than 7. So dplyr, you can still do it in Python. The other big thing is that, and I didn't realize this, RPy2 in the past year has really completely overhauled its backend. So if you don't like the cell magic that I showed you on Tuesday, you can just do without it now, because RPy2's backend allows you to just directly import R functions and directly import entire R libraries into Python, meaning that you can pretty easily do R while in Python. With some exceptions where certain libraries might throw you bugs if certain proper R dependencies haven't been installed properly and so on and so forth. But just to give an example of this, we're going to be importing the R objects function from RPy2. Again, RPy2 needs to be installed for this to work. If we use the robjects.r command, we can take any R command, just like seek, and just run it, and it should run in Python, no problem. And if we want to install an entire library, like LME4, instead of actually having to do the R magic like we did on Tuesday, we can instead take the entire LME4 library, store it as this new variable, LME4. When we run that, it's going to take a second to load in the large library, but we should get a docstring that basically tells us that we've been able to effectively load in LME4, and we should be able to start calling all of the standard sort of LME4 functions that you know and love, like glmr. So the beautiful thing is that more and more nowadays with Python is that you really don't need to choose between R and Python. You can easily take all the things you've learned in R and apply it to Python, or vice versa. So thank you all for your excellent questions, because I didn't know you could do that, and now I know you could do that, which makes me really want to go back to R more. The one thing I will say is that some of these packages are a little new and might cause some weird bugs with pandas, which I sent to the authors today. So if you called any of these functions, just be sure to restart your kernel real fast, because you'll get some weird flags from pandas as we go along with our exercises tonight. So just go up to kernel. You can do just restart or restart and clear output, whatever you want to do. We just want to erase some of those things from our cache. Okay. Any questions about what we just went through before we get started on machine learning? Great. Okay. So tonight, the main agenda is to cover the scikit-learn package. We're just going to do a really brief overview, basically really teaching you the high-level syntax, because the beautiful thing about scikit-learn is that all of the functions are basically called the same way and run the same way. Is that they basically all make use of the same 4 attributes, which we'll go through, so that if you really understand how to fit one model, you'll pretty much more or less know how to fit, at least syntactically, all the rest of the models. Obviously, you need to be aware of the various pitfalls associated with each sort of machine learning algorithm. The other thing I want to make you aware of is that there's some really excellent references for machine learning with Python, and I would recommend all these. This one actually just showed up last night on my Twitter. Somebody was really, really nice to put his entire course syllabus on machine learning and neural networks in Python. That uses Jupyter Notebooks, and you can download all of this material, and it's probably a way better demo. But the other thing I will say is that I'm not saying that I don't own a PDF copy of this book. I'm not saying that if you emailed me, I would send you a PDF copy of that book if you wanted more material. I'm not saying that at all. Okay. And the other big thing I should say is that scikit-learn, in terms of Python packages, has to be one of the best documented packages. they have not only incredible examples on how to run their code, but just really, really wonderful examples about when to use certain algorithms and when not to use other algorithms and how to run and generate things. So like their documentation is just beautiful, and I would really, really recommend checking it out if you want to do more machine learning in Python. Okay, getting started. Like I said, high-level syntax. The important thing to know basically is that every main algorithm, every main method we'll be running with machine learning through scikit-learn basically will be its own separate class. In the same way that strings were a class or lists were a class where they had their own sort of built-in functions, that's exactly what's going to happen here. So every time we load in a pre-processing command, or we load in a support vector machine, or we load in a neural network, all those will be their own classes, and all those will have their own built-in functions. The really nice thing is that most of these functions will have the same 5 or 6 attributes, which means that, again, if you know how to use one of them, you'll know how to use all of them. Very quickly, those are fit, obviously. So you're going to take some data, you're going to fit a model with it. Transform is once a model is fit, you're going to take some observations and you're going to transform it into a new space, be that dimensionality reduction with PCA, or potentially predicting new variables based off some other observations. Fit transform is just basically a shorthand for doing these first 2 steps just together. Predict, again, once a model is fit, you want to predict some outcomes based off of some observations. You'll use the predict attribute. And score is to basically test how well your model is actually fitting some test data, right? So be it predicting the R-squared coefficient or predicting your predictive accuracy, like how many of a class did you actually accurately predict. That's what this attribute's going to be. There are some other important attributes that will occasionally show up, like get support will show up for when you're doing feature selection. If you want to know what variables you should or shouldn't include in a model, get support will return a Boolean array of true, yes, you should include this variable, false, no, you shouldn't include it. The coefficient, or the .coef attribute, basically will tell you all the coefficients of your model once it's fit, and the score attribute will return all the scores for your model. And I know this is a high-level overview, this will all become very concrete in a minute. The other important thing is that the general workflow that we're going to be doing in doing any of these steps with scikit-learn is that we're going to import and initialize an algorithm. When we initialize an algorithm, we're going to call the algorithm for the first time, and we're going to give it whatever parameters we want it to have. So penalties, sparsity, priors, whatever those parameters are. We're going to then fit a model, and then we're going to do some sort of transformation with it, either dimensionality reduction with PCA, for example, or again, predicting outcomes based off of some test data. Make sense? High level? Let's start going through it. Okay, so let's load in our data for tonight. This is totally randomized data. I made this morning. Just to give some backend, it is a nice data set of 200 observations, 10 features, and 1 outcome variable. Our outcome variable is actually now our index, so we can look at it. Just these 4 lovely little words. They appear different numbers of times. And we have 10 just random variables that will hopefully help to predict the class. So this is essentially a classification problem that we're going to be using tonight to introduce scikit-learn. Before we go anywhere, I just want to give some brief pre-processing examples. So, for example, I mentioned briefly last night demicoding. I just want to make it very explicit. So in demicoding, again, if you have a categorical variable and you want to turn that into a binary variable, so that you have a column of 1s and 0s that represents each category of your categorical variable, you can import getDummies from pandas, and I'm applying it to our index, because again, our index here is just those 4 words. And you'll see it makes 4 columns for you, where it's a 1 wherever that word appears in the index, and a 0 where not. Pretty straightforward, just so that you don't have to manually go through and do that. I also didn't go through digitizing last night, so if you want to take a continuous variable and you want to bin it categorically, digitize is a NumPy command you can use. So if we want to bin a continuous variable between these 5 bins here, it's pretty straightforward. All you do is choose what array you want to pass into the command and just your bins. So you can see, minus 5.739 is in between here, so it gets assigned to 2, so on and so forth. So again, these are very simple data transformations you might do in order to be able to start fitting models. To finally start getting away from pandas and NumPy and into scikit-learn, the first set of algorithms we'll be using are just very simple data processing algorithms. They're going to just be used for pre-processing algorithms. They're just for scaling your variables, because again, a lot of machine learning algorithms, of course, are going to be very sensitive to the scale and the offsets of your data, so you want to actually normalize all of them. Scikit-learn has a few built in, but probably the 4 most popular would be standard scaler, which is just z-scoring your data, right? So setting it so that it's mean 0, standard deviation 1. A robust scaler, which does something similar, except based off of the quartiles or the percentiles of your data, just in case you have skew in your data. Min-max scaler just sets everything between 0 and 1, or some min and max values of your choosing. And normalizer if you want everything to have a Euclidean length of 1, which can be more useful for like topic modeling. Ignore this text, because that text is wrong. So we're just going to very quickly just use standard scaler to set all of our continuous variables to have mean 0 and standard deviation 1. So what am I doing here? I'm importing it, of course. So I'm importing it from sklearn.preprocessing. So right here, this is our library. This is a submodule of that library. So the sklearn.preprocessing has a whole bunch of functions in it. They're all imported for preprocessing. That's how the library is organized. We're importing standard scaler. We're initializing it here. We're not giving it any new parameters, because I want everything to be mean to 1 and standard, set to standard deviation, or sorry, mean to 0, standard deviation 1. And like I said, we're calling the .fit transform attribute. We're passing in our data, and that's going to take all of our columns and apply this transformation. Yes?
In data.lock, in the brackets, you're explicitly stating all columns, all rows. Why
Yep.
don't you explicitly state that?
I could actually just pass that, and it will still work.
Okay.
So that was just being syntactically clear, but it syntactically works. And you can see when I call describe again, you can see after passing it through, all of our means are at 0, all of our standard deviations are 1. The main important thing I want to highlight here, so again, syntactically what's important is that we initialized this new algorithm here when we called it by its standard name and we put the parentheses by it, right? So that means another way to do this in more lines of code, for example, would have been to take SS for standard scalar and then just initialize it like this, and then to do ss.fit transform or fit, right? So what we did is we initialized the class standard scalar, so we had an instance of that class. And then once it's initialized, then we can apply these attributes, either fit or fit transform. So that's what I'm talking about when I'm saying all of these things, we're going to be importing all of these algorithms, we're going to be initializing these algorithms, and then we're going to do something with it once it's initialized. Does that make sense? Okay. Another step, this is obviously a really small data set, so really we probably don't need to do feature selection, but I know when I generated this data set that half the variables are uninformative, so we're going to do feature selection anyways, just so that we can demonstrate it. One important topic I wanted to go over, oftentimes you don't really have to do this in machine learning, especially if you have penalized models, but it's just worth pointing out because it's useful for statistics broadly. The variance inflation factor, I'm assuming it's been covered before? Yeah, okay, great. So, right, variance inflation factor is a really great way for testing whether or not you have collinearities in your design matrix, or which, if you do, can lead to really wonky coefficients if you're fitting a linear model. So, really quickly, let's just check and see how our data looks. One way to do that is to just take the heat map of our correlation coefficient, because one form of collinearity is basically if two variables are highly correlated. That's one way of inducing collinearity in our data set. You can see that it looks like we are starting to get some high collinearity in our data. Alternately, we can import from stats models the variance inflation factor command. So that's from stats models, .stats, .outliers influence. It's lengthy. And we're going to get this new command, variance inflation factor. The exog flag is just our design matrix. And the exog for exogenous index just tells us which column we want to test. So that's a numeric input. So that'd be, because again, Python is 0 index, we wanted to test the first column of our design matrix, that'd be 0, second would be 1, third would be 2, so on and so forth. So we're going to use a list comprehension to just very quickly go through and test the VIF for all of our columns and our features. You can see that doesn't look too good. One of our features is highly collinear with a VIF of like 50, which is really no bueno. You want it to be closer to 5, if anything above. So one thing we can do is just very quickly, we can just drop that variable from our data frame, and we can recompute it and check and see whether or not it looks like our data is no longer as collinear, and it's not, which is great. The other parts of feature, so scikit-learn has a lot of feature selection algorithms. So if you have, 100,000 observations and 10,000 features, and you want to maybe pare that down to something like 1,000 features, scikit-learn's got you covered. They typically are clustered into 3 types. So there's univariate testing, where basically you're just going to test each feature independently. There's model-based approaches, where you'll fit some sort of machine learning algorithm to it, and you're going to select the most important features. And then you can do iterative or model building approaches. I just wanted to show you some of these functions. So there's a few for univariate selection, like select k-best to select the top 5. Select percentile, choose the top 10% best variables. Select FDR for select false discovery, or select by false discovery rates to perform significance testing on every single variable, and then do multiple comparisons corrections with the false discovery rate, which whatever survives stays in your design matrix, or stays feature. And then select family-wise errors, the same thing, just with a family-wise error, multiple comparisons corrections, so slightly more conservative than the FDR. The really important thing to know is that if you want to import any of these, all of these live inside sklearn.featureSelection. So we're going to just quickly run through a univariate example. So we're going to go ahead and import from sklearn.featureSelection the select percentile. We're going to import a few of these just to show you the syntax, but we're just going to run the select family-wise error one. So again, here we are, first step, we're initializing it, and we're saying we want to set to an alpha level of 0.05. We're going to fit it. We're going to fit this algorithm to our data. So the flags are what are our features. So our data is our features, and our outcome variable, the thing we're trying to predict, is our index. So we fit it here. And then again, we run this getSupport attribute, because getSupport gives us a Boolean array telling us which things survive the multiple comparisons correction and should be included in the model, and which ones do not. If you don't like calling everything in 3 lines, scikit-learn supports chaining, so we can just throw this all together into one long command, and we can do all the steps all at once and get the same exact output. So, and then we can just use what we got before to just reduce down our data, and you can see we went from 10 columns to 4 columns. So now we've removed 6 columns from our feature list. So I'm not going through tons of examples of feature selection, because I'm assuming that's been covered probably in the data mining course. But I just want to point you guys to the syntax again. Just it's the same thing. We're importing an algorithm, we're initializing an algorithm, we're fitting it to our data, we're doing something with it. Okay. Same exact thing here. Scikit-learn has a ton of unsupervised learning algorithms. So you can do PCA, MDS, K-means, agglomeratory of clustering. There's tons of Gaussian mixture models. There's tons of things you can do. We're going to go through a simple PCA example because it's the simplest and easiest one to get through. Same exact syntax as before. We're importing the function, and PCA is going to live in the decomposition submodule. We're initializing it and telling it how many components we want to break down our data to. So I just want to break it down into the first 2 components of our data so that we can very quickly visualize it. We're fitting it. So again, we initialized it here, fitting it to our data. And then we're going to use the transform, because we're going to put our data through the transform attribute to scale it from 4 dimensions to 2. So you can see, the other nice thing about the PCA thing here is that it actually also gives you an explained variance ratio, so it can tell you of the first 2 dimensions how much variance of your data were you able to explain, which is nice. So we got about 40 and 25% of the variance of our data from the first 2 components alone. And you can see when we reduce down our data, Our data 2D is now 200 observations, which is what we started with, but now only 2 columns. So we were successfully able to reduce it down. We can pass this into a data frame and then just very quickly plot it to show like, oh look, our data seems to have some level of clustering, right? The Foxtrot points seem to be nicely separated from the Yankee points, and the Tango and Hotel points seem to be maybe a little less segmented. And again, going back to what we talked about just in terms of quick plotting, with pandas, all we had to do was just index into which columns we wanted to plot, and we just passed that to the scatter function, and it was able to do all, just obviously plot it all onto one canvas. Okay. I know that's really short. That's all I'm going to cover about on supervised learning. We can actually go through a ton more examples in like 20 minutes if we want to do more. In terms of supervised learning, obviously one of the most crucial and important steps is dividing your data up between the training set and the test set, right? Because we're going to want to start fitting more complex supervised learning algorithms. So to do that, we need to be able to actually avoid overfitting by fitting only some of our data to the model and then seeing how well it generalizes to a test set, right? Hopefully everybody, yeah, familiar? Okay. The main function to do this with scikit-learn is the train test split command. So this, again, lives in the model selection submodule. So we're going to import it from sklearn.model_selection, import with train test split. Okay. We're just going to divide up, for clarity, we're going to divide up our data set into our X variables, our features, and our Y variables, our outcome. And the syntax for train test split is really, really straightforward. We're just going to give it our features, our outcome. We're going to say how big do we want our training set to be, what fraction of the data. You can also give it an integer to say how many actual rows or how many actually observations. We can give it a test size. You can specify one or the other, and it will figure out how it should split. In this case, I'm just making it very transparent by specifying both. But for example, if I only specify test size is equal to 0.2, it would infer that train size should be 0.8. And I'm just setting a seed with random state. What that's going to do is that it's going to split up my data into 4 new arrays. I'm going to have a matrix of all of my training features. I'll have my test features. I'll have my training outcome variable, and I'll have my test outcome variable. And if we run that, you can see originally our data was 200 rows by 4 columns. We said 80%, so that gives us 160 rows in our our training data, and 40 rows in our test data.
I know in R, some of my questions anyway, advise against making variables named like X period train, because it starts to interfere with some functions. They always prefer X underscore train. Is it the same in Python, and we should avoid that?
Yeah, so actually you really can't even do that unless, I mean, I guess you could. I mean, so whenever you, whenever you do dot in Python, you're trying to index an attribute, so it will definitely mess with things. So yeah, I would really try to avoid dots wherever possible. So the real convention in Python is the underscore. Every once in a while, you'll see me doing something Python inappropriate, like camelback or camel case, but really the classic sort of preferred aesthetic in Python is, you know, split everything up by underscores. Okay. Scikit-learn, being the full machine learning package that it is, has tons and tons and tons of supervised learning algorithms implemented. If you want tutorials on how to fit a ton of these models, in fact, every single one of these models in Python, go through the notes document. We're not going to go through that, otherwise you're going to hear me talk for 4 hours. But if you want tons and tons of examples of all of these algorithms being fit in Python to different data sets, go through the module 3 notes, Jupyter Notebook. That's using 3 different data sets and tons of examples, tons of visualization, tons of different tests, tons of plotting with Seaborn, tons of data frame manipulation. So again, if this feels like it's going really fast, it's because I want to start doing some in-class demos with everybody. To just further just show that the syntax in scikit-learn is exactly the same, we're just going to fit a very quick support vector classifier, so a linear SVC, that, as this table suggests, so for all these different families of algorithms, I've listed where they live in sklearn. So again, if we wanted to fit the support vector machine that lives in sklearn.svm, so we're going to take linear SVC. So again, same exact syntax as before. Here we're initializing it, so I've imported it here. We're initializing it. I'm giving it an L2 norm penalty. I'm giving it a regularization coefficient of just 1, which is its default. If you wanted to have induce higher sparsity in your data or have higher regularization, you'd put C much higher than 1, maybe like C of 1,000, C of 10,000. If you wanted to have very little sparsity induced, you would put C of maybe 10 to the minus 4 or something. That's not going to make a huge difference here because we have 4 variables. But if you had 10,000 or 10,000 features, that might be more important. I'm assuming that makes sense to everybody. If it doesn't, I can go through it. But it looked like most of you have taken the data mining course. Okay. So let's actually run it. So here we're initializing it. Don't undo. Here we're initializing it. Here we're actually going to fit it. So we're passing it our trained data. So we get a new fit object. And now we're going to use the new attribute that we haven't used before, fit.score. In fit.score, we're just going to show how well our model is actually performing. So we're going to pass it our training data to see how well it actually fit our training data. And that's split by our training X matrix and our training Y array. And then we're also going to pass it our test data to see how well it does. You could run it. So we got about 75% accuracy in terms of classification performance for our training data, and not the best, not the worst, about a little below 60% on our test data. It's a messy data set, and I mean, it's well above chance of 25%, which is, I guess, good. The other thing is that I'm showing you now the predict attribute. So for predict, once you have a fitted model, you can pass it some observations, and it will give back to you what it predicts, what class it predicts that it should belong to. So here you can see the predictions that it's making, these lovely little words. We can also compute a confusion matrix real fast, just to quickly look and see where is our model really messing up. So I'm importing just the confusion matrix. I am actually going to just put our confusion matrix straight into a data frame. So I'm actually taking the confusion matrix command right here. All it takes is the predictions from a model and what the actual true classes were, what the true labels were. And otherwise, I'm just telling it what our rows and columns should be, which should just be the unique set of our indices, right? So Foxtrot, Hotel, Yankee, and Tango. I'm putting it into a data frame. I'm normalizing it so that it sums to 1 across the rows. And you can see, so we're getting pretty good performance on Foxtrot, and we're getting pretty good performance on Yankee, and we're getting a lot of confusion with Hotel and Tango, which is not to be unexpected, considering that we look at, can I drag it down? Oh, beautiful. All right, fine, I'll do this. Also, you can do this with extensions. But if we look and see, you can see that, okay, so Yankee was doing well and Foxtrot was doing well, but Tango and Hotel were not clearly separating. So that fixed our confusion matrix pretty well. Okay. Obviously, when you are training up different models, you don't want to just do one fit of the data. You want to do cross-validation because you want to make sure you're using the right level of hyperparameters, but you also don't necessarily want to make a training set, a validation set, and a test set, right? Because that's very inefficient with data. So we're going to want to do the cross-validation method to try to find out like what parameter settings are best for fitting our data. So sklearn or scikit-learn has a ton of different cross-validation algorithms that we can use. Of course, it has things like k-fold and leave one out. It's got some other nice custom ones like shuffle and split. So you can define just arbitrary sequences, for example, a training set of 80% of the data and a test set of 20%, and I'll just generate as many random splits obeying those ratios as you would like, if that makes sense. There's also stratified cross-validation techniques. So if you have what we have here, which is a category classification task, and our data is actually stratified and is actually not fully balanced, maybe you don't want to do pure k-fold because you actually want to make sure that you are balancing the ratio of observed data across your training and test sets. So you can do that with stratified k-fold, you can do that with stratified shuffle and split. So there's all different sorts of cross-validation algorithms that you can immediately import and use. So we'll show you how to use them real fast. So again, all of the cross-validation algorithms live in the model selection submodule. So we would just do from sklearn.model selection, import stratified shuffle and split. To show that there's many, many more, for example, we could do from sklearn.model selection, import, just hit tab, and you can see there's a lot of different things in here. So there's group k-folds and leave one outs and random permutations. So there's lots and lots of different algorithms in here we can use. But we're just going to go with the stratified shuffle and split. So again, what this is going to do is that obeying our stratified data, obeying the fact that we have class data, it will make, in this case, 5 splits of our data, where 80% of our data is going to be assigned to the training set and 20% of the data is going to be assigned to the test set, and I'm just setting a seed here. What does this actually do when we run it? Oh, no, it's because I didn't run this. Should import it first, guys. There we go, okay. What it actually spits out is really, really straightforward. It's going to just spit out an array that looks like this, which just tells you the indices of the data it's assigning from your X matrix, the indices that it's assigning, or the rows that it's assigning to your training set, and the rows that it's assigning to your test set. So the shape here is we're printing out train underscore IX, so those are the indices of the rows that it assigned to the training set. Test underscore IX is the rows that are assigned to the test set. And you can see the train set is always 160 because that's 80% of 200. It's always 40 because that's 20% of math. And just this is what it's giving out. It's just arrays that are just indices. So you could use this, for example, to index back into your predictor matrix if you want to start iteratively fitting models. So we're actually going to just do a quick example of this. Actually, we'll do 2 quick examples. The first one is, as you guys probably know, you should expect differences in your performance between your training score and your test score, your training performance and your test performance, as the ratio of data that you assign to your, for training as it gets larger and larger, right? Because when your training sample is small, you're gonna overfit. So typically what happens is that as you start fitting more and more data, your training estimate will go down. But inversely, because you're including more and more data, your data the model that you end up fitting should be more generalizable, so your test performance should start increasing. So you should see a decreased performance for training and an increased performance for test. Does that make sense? Okay. So let's actually just quickly demonstrate that by using this cross-validation technique. So up top, I'm just defining some parameters that we're going to use to make this example work. So for example, I am going to try 13 different splits of the data. So I'm going to start with 20% of the full data set for testing, or sorry, for training, all the way up through 80% in increments of 5%. So we'll go 20, 25, so on and so forth. I'm going to do 25 splits of the data, or I'm going to do 25 iterative shuffles. So I'm going to fit the model 25 times for each training size. And my test size is always going to be 20%. Here I'm just pre-allocating space for our scores because we're going to compute the training score and the test score for every split of the data. And this just kind of clunky for loop is just to really demonstrate how, piece by piece how we're going to do it. So we're going to iterate over all the training sizes. We're going to re-initialize stratified shuffle and split with every top for loop because, again, we want to assign different training ratios. So Its n splits is always going to be 25. The train size is going to vary by for loop. Test size will always be 20%, and we're going to set a seed. And then remember, as of before, it just spits out these indices. So it's just another way, it just shuffles and reshuffles our data so that we can keep fitting the model. So that we can look and just see in general how does our model fit change as the training size changes. And the same exact things before, we're defining our indices. We're fitting the data by applying the indices that were assigned from stratified shuffle split to our feature matrix and to our outcomes. So again, just applying those indices. Then, and that's to fit a support vector classifier. Then we're predicting the training score, and we're predicting the test score, and we're just storing it all together. So if we run that, it should take a second. You'll see we get a matrix that looks like that. It is a three-dimensional matrix. It's the number of tests or training sizes that we did by the number of splits that we did by the three metrics that we looked at. Let's do a little work with pandas to get this into a long list format so that we can very quickly visualize it. So the first thing that I'm going to do is I'm going to put it into a data frame. To do that, I'm reshaping our data so it goes from being a three-dimensional matrix to a two-dimensional matrix. So I'm collapsing across the number of training sizes that we looked at and the number of splits that we did.
Where did you go to split that cell? Sorry.
It's right here with performance.reshape.
No, I mean in the actual number.
To run performance?
You set it up so that it's a separate code box.
I'm sorry,
I
yes.
didn't see that happen, I'm sorry.
Edit, split cell.
Oh, thank you.
Mm-hmm. And there are also key commands for it, but I can't remember that key command for the life of me. So we're just reshaping it into a new data frame, which looks like so now. So one column is the training size, one column is the test score, or train score, one column is the test score. We're next, and just doing edit split cell. The next thing we're going to do is we're going to melt the data frame. And what we're going to do is we're going to melt it, which means that we're going to collapse two of the columns. We're going to preserve the train size column, but we're going to collapse across the train score and the test score so that that ends up being merged into one column. So the variable I want to preserve goes into my ID variables flag, and then everything else is going to get collapsed into one column. I'll explain why I'm doing this in a second. But just know that I'm going to rename that column model, and I'm going to rename a new column score. So let's look at that, what that actually looks like, so that makes sense. I ran it. You can also merge cells back together. So let's look at what performance looks like now. Okay, so it's now three columns again, but you can see now we have two new columns. So we have train size like we did before, but we have model. Model is going to tell us what sort of score we're looking at. We're looking at the training model, we're looking at the test, or the test score, the training score. So if we look at performance.model.value counts, for example, we've got 325 of each. So we've got 325 training scores and 325 test scores. And then obviously score is just the score for that iteration. Because we just put that into long list, that's now going to play, and is it clear why that's long list? It's long list because I've stacked two different variable types on top of each other effectively. So train now represents both the training and the test columns, and so score has a mixture of both train and test, and I know which one is which because I can use this model column. Okay, that's long list. Melt is very, very useful. R obviously has that too. But the reason why it's really nice is because once it's in long list, Seaborn, the visualization package we talked about, plays really, really nicely with long list data because if you give it a data frame specified under data, it's going to look for three things. It's going to look for whatever you want to plot on the x-axis, it's going to look for whatever you want to plot on the y-axis, and it's going to ask you if you want to split the data by a certain variable, which is going to be called hue. Here, we want to plot two lines showing how performance changes with different training sizes, but we want to split our data by whether or not it was the training score or the test score. So that variable was defined as model. So really, this code of this line of code right here is actually Q is equal to model, X, Y is equal to score, X is equal to train size. And that's it. That's just one line of code, and then we'll get this. So one line of code gives you out this nice little plot, which shows you that actually conforming to our expectations, as our training size increased, our training score decreased, and as our training size increased, our test score increased, which makes sense because it means we're no longer overfitting and we're generalizing more. So beautiful proof of concept, small working example, and also, as I was talking about on Tuesday, why getting your data stored into long list is so helpful for visualizing with Seaborn, because it just loves long list data. Okay. Any questions on that example? So otherwise we'll do one more quick example just to show you further cross-validation techniques, and we'll open the floor and start doing some examples. The other really nice function that sklearn has, and probably it's one of the most important functions that it has, is this cross-validation score function. Let's actually open it up and see what it does. Basically, it replaces that for loop that I just did. It will do iterative cross-validation for you in one function, and it will spit out all the test scores so that you can very quickly test and see what model parameters should you be using to actually best fit your data. So what it takes, its flags are pretty simple. It takes some estimator, which is some machine learning algorithm, so that could be a linear support vector classifier, or it could be a lasso regression, or a ridge regression, or it could be a neural network, whatever you want. Takes whatever your features are, takes whatever your outcomes are, and it can take some other things that we're typically going to ignore. But the really important flag right here is that it has a cross-validation flag. Cross-validation can either be specified as an integer, and it'll automatically perform whatever fold cross-validation you specify. So if you specify CV is equal to 5, it'll do 5-fold cross-validation for you, 10 for 10-fold. Also, if you give it any one of those cross-validation algorithms, it will automatically compute the test score based off of whatever cross-validation algorithm you want to use. So be that some custom k-fold, or some custom leave one out, or some custom shuffle and split, it'll automatically do that for you. So this CV flag is super nice, because now you can not only fit, you can iteratively go through and compute multiple tests, or you can do cross-validation of an algorithm. You can specifically specify all in one line what sort of cross-validation technique you want to use. Okay. So let's actually just go ahead and do that. So before I mentioned that linear support vector classifiers have a regularization parameter. It's not a huge deal here, because again, we have very few variables. But for example, if you had fewer observations and many features, maybe you would want to force many of your coefficients to go to 0, right? You'd want to have some sort of penalty term and induce sparsity in your model. That would be your C parameter, or your regularization parameter. So just for an example's sake, we're just going to show testing out a few different regularization parameters. So we're going to do 10 to the minus 2, 10 to the minus 1, 10 to the 0 or 1, 10 to the 1, which is 10, or 10 to the 2, which is 100. We're just going to test out a few different ones and see how that changes model performance. So let's go through it. So I'm defining which regularization parameters we're going to be testing here in C params. I'm going to say that here we're going to be doing 10-fold cross-validation on our data, just pre-allocating space for our scores. Remember, and we're going to be using this linear support vector classifier again, but we're going to reinitialize it every time, because we're reinitializing it with a different regularization parameter, C. And then we're going to pass that to cross-validation score. So again, we're passing it the algorithm we're going to use, we're passing it our data, X and Y, and we're telling it what cross-validation technique we want to do. In this case, we're just doing 10-fold cross-validation. Go ahead and run that. Here, performance is another 3-dimensional matrix. That's the number of parameters that we have, the number of cross-fold validation that we did, and just the C parameter. It's basically storing the C parameter is one of the columns here, and the other column is the actual score for that model. And we can do the same exact thing. I'm going to reshape this matrix, again, using the same code that we did before, from a 3-dimensional to a 2-dimensional matrix. And then I'm just going to pass it to a different Seaborn function, swarm plot, which is a lovely named function. All it does is really good for plotting categorical data on the x-axis or on one of the axes, and a continuous variable on the opposing axis. And one thing that's really nice about it is it prevents data points from overlapping on top of one another, so it'll scatter them out for you so that it's actually pretty easy to see where all your data lies. And again, what we're measuring here with swarm plot, or what we're going to visualize with swarm plot, is just how does our model performance change when we try different regularization parameters. And the answer is, doesn't change dramatically. Certainly you get wider skew, but I mean, maybe it's a little better here because the density is a little higher, but it doesn't really matter. You wouldn't really need to change that anyways with 4 variables. Okay. That was an hour. What I'd really, really like to do is actually start demoing with everybody. I want to give you guys an opportunity to actually work on code in class now that we've gone through core Python and pandas and all this stuff. So to do that, there's a number of different ways we can do this. I'm open to whatever. We can, as a class, start working through examples. We can split up. You can talk to your neighbors. You can be a hermit like I normally am and just work on examples. But I want to just go through some of the data sets that we have available in Module 3. What we have is, I mean, first of all, we have the data set I just presented, which is this random data. We have the very classic iris data. It's the super classic. We're going to classify 3 different types of iris flowers. It's a great classification problem. They cluster very cleanly, so it's actually a really nice one. It's a great ground truth one. I think it's 3 types of flowers. I should know because there's a README telling me what's in this data set. Oh, look, it's 3 types of flowers. We have a diabetes data set, which is not a classification data set, it's a regression data set, so the outcome variable is a continuous variable. So basically we have 10 different health baseline variables, and you're trying to predict how well a patient is going to be doing on some outcome measure of their diabetes a year later. And there's actually more fun. I should go through this one first. There's a wine data set, which is actually a really cool data set that we found. It's 11 features and 1 outcome, which is its quality, so whether or not it's a good or a bad wine, based off of all of these different things. Also, it's split by red and white wine, so another thing you can do, for example, is based off of the attributes, you can try to predict as a classification using logistic regression whether or not, or logistic classifier, whether or not it's a red wine versus a white wine. So it's both a regression problem, so you can regress on its quality, or you can try to classify whether or not it's a red or a white wine. And there's tons and tons of data here. It's like, I think, nearly 8,000 total observations. That data set's really cool. A little closer to my heart is a really messy, and I totally wouldn't recommend going through it on a first pass data set of 4 different types of humans, healthy controls, patients with schizophrenia, patients with ADHD, and patients with bipolar disorder, and several hundred responses to different questionnaires, talking about what sort of psychiatric symptoms they may be experiencing on a whole bunch of different varieties. And this is a really challenging classification problem, but you can try to predict whether or not they are healthy controls, whether or not there's patients with schizophrenia, patients with bipolar, patients with ADHD. It's a really challenging data set because it's incredibly messy. It's my favorite topic because the DSM is terrible, but that's a side story. I'm not hesitant to relinquish power, but I'd like to relinquish power and see what the group feels like doing. Do we want to work on something together? And I get feedback from you guys, like, what sort of pre-processing steps should we do? What sort of feature selection should we do? What sort of algorithms should we try out? So we could do all as one. People can break up and load in some data sets, or you can apply it to your own data, and that's totally cool. What say you?
Raise your hand if you want to do something together in class.
Thanks, Megan.
Okay, raise your hand if you want to group. Class has it. A lot of none. Raise your hand if you crumpled up your master's degree or placed it Hug me when your soul once was. And there it is.
All right. Of all those data sets, are there any of them that sound remotely more interesting than not interesting? Wine. Yeah, there we go, of course. You guys are the best. The other reason why that's great, it's a great choice because that's this one. And I've already gone through that, and we can like demo tons of things, but maybe you should hide your eyes for just a second so that I don't show you all the code. Or maybe we should show you all the code, but we're not gonna look at the code. We're just gonna ignore the code. Actually, so the wine example is the exercises data set that you guys can do, but like we should probably just go through it in class. That seems like a good idea as well. Okay, so here's the thing. It's a data set, 2 different types of wines. There's red wines and there's white wines. It's all Portuguese wines. I don't think that's important, but now you know. We have 11 different attributes. So if we go to this README, we can look at the sorts of things that we'll be working with. We have different measures of its acidity. We have different measures of its sugar content. We have different measures of its sulfur content, and how alcoholic it is. Spoiler alert, how alcoholic it is really important. Hilariously. So first things first, right? So the first thing we'd have to do, oh man, I really wish I had. All right. In that review thing that we sent around, where you guys can critique my performance, somebody said we should put in a 5-minute break. Can we do a 3-minute break so I can quickly make a new version of this that doesn't have the code in it? Everybody can go use the bathroom. You guys are the best.
Except like all time. So your configuration. That's okay.
Yeah, I stopped here for a piece. I was in a group of people.
That's still good.
They were like, they smashed a lot of sarcasm. I got like a bit of work.
I was thinking, I just
Why still work? Yeah. Yeah. I started doing that for first I have like 6 months already. Just like, this is your project, just 6 months. Like, oh, this person wants to done something, so you can let it be done, but otherwise. Oh, and if you want to like contact the data team, have some sorry coders, you can have to like have a bit of that work, but other than that, that's it. Yeah, for what? Well, my old job was like so day to day, whereas this last time I played a long time, although it's going to make it harder to like do pieces for this. Oh yeah, we'll get maybe like, why are you doing this? I was going to do it next project. Well, I can't take the data down. Just find someone that's yeah, I wanted to try to
long day, that's all.
adding an additional factor to our
I have a project for which I can't actually use web scraping techniques. I have to actually find information and record it myself.
That's the worst. That's the most frustrating.
That's what I've been doing all week, and it's just got like my eyes are crossing.
It's just like mind numbing. Yeah. Oh gosh.
That's part of the oversoon.
Yeah, that's good. This everybody is pretty comfortable with these like concepts, right? I didn't like just gloss over a ton of things and it was like, oh god. All right. You guys seem, well, I mean, so, I mean, I should really explain, like, my stats background is really as applied to very specific neuroscientific things, so I think in terms of at least, definitely with probably regard to machine learning and data mining, you guys are probably miles ahead of me.
I'm not, I guess kind of machine learning things in general, so that's fine. I know what they mean, I can follow what you were talking about.
It's great. It was great. So, because when we were doing this, I was talking to Professor Eyrick, who was the one who hired me, and I was like, "So you really want to spend a lot of time focusing on this? I should really say I've never really done this." And he's like, "Can you teach yourself?" And I was like, "Yeah." And he's like, "Okay, cool, all right, fair enough."
I was about to say, yeah, that's what we did anyway.
Yeah, that's yeah. I think that's a majority of it.
I actually went over, I don't know why, I was nostalgic for the class, so instead of like pull up some of my old homework assignments, I was just like, oh, good lord, how did I accomplish any of this?
Yeah, they're just like a giant blur. It's like, I just like know the words like random parts and stuff, but
Actually, the one that for some reason I had the least clear memory of was PCA. I like look back at that now, and it's like, I need to do that. How?
I think my brain
Oh,
is like a
you might not have.
right after this.
Can I check something real fast?
Yeah,
Does it? Yeah. Does it?
Oh yeah. That was definitely especially for data man. That happened.
That's very bizarre.
Obviously, they're like exposing you to lots of examples that you feel like always works, but it's just crazy.
You have it.
And then it has like those examples like.
So he like laid it on how he wanted it, like, and I was like,
And
finally someone hand drew the graph. Yeah, because like for our final, he was always like talking about like include like drawings, how you want it so like being laid out.
Yeah, like if you have any hand drawings of your like, yeah,
Oh,
like put it in
that's
this design and like no one ever
For
did.
the final, like legit really wrote on the boards, drew it.
Oh, I've seen that picture.
And then yeah, I like put it in
Everything needs a rough draft, right? Which I assume is the point of that.
Oh, we just need to update your SKR. That's all we need to do. So if we go.
Yeah. Are they all 5 cents in the
Install, upgrade.
That is still one of them. Yeah, exactly.
Yeah, no problem, of course. Yeah, it's really, yeah. Nice to meet you. Yeah, of course, it was no trouble at all.
Is it also 4th dimensional with that, like, you can do visualizations need the time? Yeah.
Yeah. Virtual reality.
That's what you need the 4th dimension for, though. Resolving that particular problem. If I could time travel, I can tell myself to work out, I still wouldn't. So I have no reason to believe I can't time travel yet. So there, my own paradox is solved.
Yep. Usual neck cracking. Is that everyone? Am I missing people? This likes like people. Three. Okay, that's enough to wait. Right, 3 is. Yeah.
Oh, we have one so far. We still have to work on it. like it's extra quality anymore. It's like the worst version of Friday. It's like, oh yeah. Oh, even better. My sister did it too. So Fridays are bad. I one other. Saturday I'm still doing something, so I have to leave
Are any of you Westwood?
I kind of wish it
I stopped Westwood, but I was curious about the Seaboard package.
Yeah.
And that's what SNS is.
That's actually Sam Seaboard?
Norman.
It's actually named.
It is.
Holy crap, that's
Wait, are you serious?
Yeah, I looked it up because I was like, why is this called Seaboard? It's not a snake hunt. It's not a python hunt. Why would they choose?
I had no idea. That's the
It's
best.
actually for Sam Seaboard,
That's so
which makes
cool.
sense because he was like the pretty boy ever,
Right.
and it's data visualization.
You know what? That's fantastic.
This makes me love this language all the more now.
I mean, I made myself remember it by association that way, but I didn't realize it. That's sweet.
Yeah. I expected to find something I didn't expect to find.
My first semester,
Oh, it's awesome.
because I was like number 4 everybody.
Yeah, I don't know if you can see the part time.
I'm done. I was gonna.
And I want there to be some way to tell Rob Lowe that he is a Pakistan.
We should collectively tweet at him.
Yeah. Rob Lowe?
Bravo, Sam Seaborn.
Sam
Here he is
Seaborn.
again. Yeah.
The Seaborn package is named after Sam Seaborn, Rob Lowe's West Wing character.
So the shortcut is SNS, which is his character's initial, so it's even more weird on it.
Holy crap.
I could never figure out why it was SNS because it's like there's no,
Sam
yeah.
Norman.
The convention is SNS, and I was like, oh, I'm just gonna go for it, but oh my god.
Yeah.
Well, I assumed SM was just Seaborn.
Yeah.
That's what some of the reference I was going to get.
Yeah, I don't know. I guess Seaborn. Is that people? Am I gonna make you count again? They're like 10 minutes.
It's 8:15 on Thursday.
All right.
They might have just bailed.
That's cool too. Good for them. Initiative. All right, let's get back to it. Before we jump back into some other scripting stuff, I just want to quickly show somebody very rightfully requested just a quick demo of working Python from the command line and doing scripts outside of Jupyter Notebooks, which is incredibly important. So the other thing that we put into the module 3 for you guys is this new folder called command line, which is 3 very basic command line scripts. The first one is literally just the print hello world. It's the simplest one I can demo for you. So I'm going to go to a terminal. There we go. And I'm already in this folder. Well, actually, I'll now be in this folder in a second. So that's why I don't have to call an absolute path. So I'm in the folder with these scripts. Otherwise, you'd have to call it with an absolute path. But all you have to do with terminal on a Mac, with the Anaconda prompt on a Windows, is just do Python and then a path to the script. So hello world, it works. So if you need, for whatever reason, to call Python from the command line, which maybe you do if you're on a cluster system, like I used to be at my old job, that's how you do it. I can show you a few more basic things real fast. Let's say you want to have arguments be given to a script from the command line. The most simple way to do that is with the system module. So you would import sys. It's got a little flag right here called sys.argv that just reads in whatever arguments were associated with the command line call. So I'm just going to read in all the arguments here. So if I go back to the terminal, this new script is called command line 2, and I'm just going to put in a bunch of different arguments like hello class, this is Sam. Oh, I called 1. There we go. So you can see I called it with a bunch of attributes right here, and it read them in sequentially, and it printed them back out for me. So you can use Python to read from the command line and call functions from the command line. If you want to be really classy with your coding, you can actually start defining your own full command line functions through Python. with argparse, so argument parser. The syntax looks kind of gross. I promise it's not that bad. Basically, you initialize a new argument parsing, and you just basically give it a bunch of arguments to look for. So I'm saying look for -i or --in, do some things with it, like for example, store this new variable as the source. Like for example, if I wanted to put a path to something, and as the help for this function, I'm saying source directory, I could do that for a target, and I could do it for this other flag that basically says, if I run this command with --silence, don't print anything out. Just ignore everything that's happening on this flag. Don't worry too much about the details here because it's a lot of copying and pasting, but just to show you that it works. First of all, now, if I call this, and I don't do anything, it will tell me it needs some of these following commands to actually run, which is a nice feature. It will also interpret --help now, and it will print out the doc strings for everything. So it automatically will start configuring an actual full command for you. But now let's do the fanciest things. We'll do -i, which is our in path, and out for our out path. It'll just go ahead and print our source and our targ. But like I said, if I do --silence, nothing gets printed. It tells me to shut up. That's a command line tutorial for you. So again, there's various reasons why you might need to run Python from the command line. If you have to SSH into things, it can be really difficult to use Jupyter Notebooks. So if you have basic scripts just stored for you, it's really easy to call them from the command line if you need to SSH in or SFTP or do whatever you need to do into like a work server or something. So we can talk more about that if you guys are interested. But we got wine to get to, so let's do that. So these are the exercises. It's a lot of cool little mini examples to do here. We're going to work with this wine data set. I think what would make sense is that, one, I should say, there are solutions. So there's a lot of code already written out. But I think what would be good, we're just going to define some problems. I'm going to give everybody a few minutes to work on it, and we'll go through it together, if that sounds like a reasonable way forward. So obviously, the very first problem that we're going to have is that we need to read in this data into Python somehow. So I've shown you a number of examples on how to read CSV files in. Why don't you guys crack to it? Oh, and pay attention to that hint, because I say it's a CSV file, but it's actually separated by semicolons, just to throw you off. The trickster that I am.
Now I guess the trick in everything.
I get to make faces to the camera as you guys do this. It's so exciting. Did it move or is it okay?
It turned off.
Oh, buddy.
Huh? I wonder how much we got. Oh, I just missed it. It was still going, apparently.
Still going? Oh, so it's watching me check my phone.
No, it was going. I stopped it and I touched it. So we'll just find out. That one, this is it's all experimentation. Also, I have it trained on
On the
projector
screen.
instead of on you.
That's so smart.
No, it can't read that.
Oh, what's
I
that
want
so
your
smart?
beautiful expression. We're gonna stop.
So for those of you who've got it open as a data frame, the other cool thing to try out would be maybe concatenating the two into one file, or into one data frame. Do you remember how to do that? There was an example in the module 2 notes.
I'm waiting to watch the master do it.
Oof.
That's
That's a
been a
lot
long
of
day,
pressure.
the brain's kind of done.
Oh, no, that's fair, but this is where the performance anxiety starts kicking in.
Lucky you were back then.
2 minutes. A lot of cracky bones as a 25-year-old. Got it? Yay. Megan, would you say that's time?
5, 4, 3, 2, 1. All right.
All right.
Stop computing.
Awesome. Okay. So, do you guys want me to cheat and just pull up the solutions page, or do you want me to do it from scratch? Because I have to do it with everybody.
Do it from scratch.
Okay, that's only fair. All right, so we have to read everything in. We have to make sure that it knows that it's semicolon separated. We have to concatenate everything, and I guess I should have emphasized this a little bit more. It would be good if we added a new variable or a new column to both data sets indicating whether or not it was red wine or white wines. So, just like before, we're going to import from pandas. I'm going to do read table, though we could do read CSV. And I'm also going to import the concatenate command. For cleanliness, I'm going to import OS. So I'm on a Mac, and you could live with it. I did with backslash, but I'll do the full thing. So I'm going to make a data set that's called red. And I'm going to do os.path.join. We're already in the module 3 folder, so I just need to read from the wine folder. And if memory serves, it's wine quality red for red. I'm going to get rid of this backslash here. And I need to specify set is equal to semicolon. Did this work? That's one. Let's copy and paste. We'll do the whites. It's like I'm doing my laundry. I'm really funny, guys. You should check out my stand-up. It's great. All Python related. Okay, we got it in white.
Material would you say you built that for?
What?
How convincing material would you say on average you can build that for?
Like with actual humor or just the talk? Yeah. And I'm gonna import a new, I'm gonna define a new column here. That's just gonna be the color column, and it's gonna just tell us whether or not it's a red wine or a white wine. So this is just gonna, this line of code right here is just gonna put in a new column where every single value is gonna be red. Do the same thing here. This is gonna be equal to white. So let's just confirm that these things look okay so far. Okay, that looks good, right? And then we're going to concatenate them. So I'm going to do wine is going to be concat. I need to put everything in brackets because I need to make a list of data frames that we're going to be putting together. Do red, and do white. And let's show it. Yay, okay. And to confirm, color's all the way at the end, but let's actually make sure that we got both reds and whites in there. And we have a tremendous imbalance. Got about 1,600 reds and 5,000 white wines. So I'm sorry for anybody who really likes their sulfites. Okay. We could move on to do some pre-processing, but let's just start visualizing our data. Now, this instruction is really obnoxious. You could make a very joint factor plot through Seaborn that will visualize all 12 distributions at once, but maybe we should just start with one. So with whatever attribute of your choosing of all of our columns here, what I would like for everybody to do, if possible, go to the Seaborn page, take a look at maybe their gallery or their API, find something that looks aesthetically pleasing, and maybe just plot me a histogram of one of the variables. Or if you're feeling real lucky, plot me a scatter plot of two of the variables. And if you're feeling exceptionally lucky, follow this tutorial and make me all 12 all at once. The real question is can I pee into 5 minutes? Who was able to make a plot? Anyone? Totally fine.
What was the question?
Who was able to make a plot?
I see a couple of them.
Are you all hiding your artistic talents from me?
Or they're looking at examples of plots that they could create.
That's totally it. So one thing I should say is that Seaborn is a little tricky when you're first getting started. Syntax is a little bit denser. So why don't we choose one together and we'll do a few plots together real fast. So there's a series of one-dimensional or two-dimensional plots we can do things, okay. Why don't we just, for example, start with, why don't we just look and we'll do a violin plot. We'll do some plot, similar to a violin plot, of the wines, whether or not it's red versus white, and on the y-axis it'll be its quality. So we'll see whether or not there's a difference in quality between red and white wines to start. Okay. So we've got our data, right? What did I name it? Wine? Yes. Great. Doing it way too below. Okay, go back up. So one thing we could do is should import everything first. That would be really good. So I want to remember to set my context. I set it as notebook, and I want my font scale to be something like 2 so you guys can see it, and I'll also set my style. Who's feeling moody? We're doing wines. Let's do dark red. Yeah. Megan's apparently into it. Okay. So one thing we can do, for example, is like a violin plot, maybe, to view the distribution of qualities across the two wines. So, for example, we could start, let me import all of this, with a factor plot. Let's look at that syntax. I know it's really kind of gross. So we can say what our x is and what our y is, and we can split. So maybe on our x, what we have is color, and y is quality, and we can set our hue as color again, which is sort of a weird syntax, but we just want to say that we're splitting across that. And maybe we'll set kind, which is all the way deeply embedded in here. It's really kind of a pain to find. Kind, we can set maybe to violin. Okay, so let's give that a shot. So we'll do, our x is going to be color, and y is going to be quality. Let me make sure I'm, actually, it's not uppercase. It's not, that's good. So let me tell you what I'm doing syntactically, right? So I've got the function open for you guys. So you can see I'm putting in x equal to color, y is equal to quality. I don't think I actually need to put in the hue here. We'll do data is equal to wine, and I'm going to do kind is equal to violin. Let's see off the bat if this works. Probably won't. Oh, well, it works. It's very funky, though. And that's probably because quality, as I completely forgotten, was a nominal variable and not a continuous variable. So of course it looks funky. So maybe we should do something that actually works more for categories, right? That's why it looks like this, because everything's peaked at 6 and 5. There's no in-betweens. It's all integers. So let's choose something that works better for categorical data. If you go to their API, what's really nice is they have a lot of their functions. They're split up by what sorts of plots you might want to make. So what would be a good, I guess we could maybe do a swarm plot, although that might crash this thing, but let's try. Let's see if this laptop is good enough. So remember, what swarm plots are really good at is plotting categorical variables without having there be tremendous overlap. This might get really unhappy as it tries to jitter about 7,000 points. Swarm plot, you're like usually my friends. Sometimes you're not my friends. You're not going to be my friend today? Of course you're not. So the only problem with swarm plot is because remember what it's trying to do is that it's trying to plot all the points in such a way that they don't overlap at all, which means that it's iteratively refitting everything so that it actually doesn't plot on top of each other, which means that it can be a lengthy process if you're trying to do 7,000 things at once, which in this case we are. So
Why not just a bar font? Why not just a bar font? I know it's
What?
boring, but I don't know.
What? Okay, fine. Do sns.count plot, for example. So we're going to try count plot, which will basically just do the frequency counts along our categorical variables. So on our x is going to be the quality. Y should be the count. And hue should be the color. Data should be data. Data should be wine. Okay, so it's split in a little weird way, but that was a good suggestion. That actually worked very quickly. So we could also maybe split it in a different way. So maybe instead what we should do is actually do x is actually set equal to color, and then hue is equal to quality. Oh, I can. So count, of course, is the problem here is that it's not normalized, so we're just doing the total amount, and of course that our wine is way, or white wine's way dramatically, is so much more than our red wine, so obviously the counts are much higher, but let's see if I can remember whether or not SNS count plot has a normalization. It does not. Okay, well. I have to search through the Seaborn docstrings a fair amount, so rather than watch me search through Seaborn docstrings, why don't we try a different example? Would people like to do another visualization attempt? Yeah? Okay, why don't you guys keep working for another 5 minutes on... If I can make a recommendation, maybe try something like distplot, which is a nice way of just doing a histogram. Maybe start with that. So, round 2, how'd we do? Can anybody tell me what sort of trouble, or what sorts, like what's your cognition, what's your thought process? Who's a brave soul who wants to tell me what they tried out and how it went? Rafi, did you try?
I did not.
Oh, Rafi.
Everyone here did better than Rafi. So, don't be shy.
So the other thing as well is that, so Seaborn syntax, like I said, it can be a little difficult. It plays really nicely with data frames, but there are also, we can also always go back to perhaps less aesthetically pleasing to start, but also simpler to start with some of the matplotlib stuff as well, right? So this is a quick one I did with Vectorplot, just showing the difference of how alcohol influences the quality of line ratings. But we can also maybe do a different one. So maybe we can just try really simple. I'm just going to help. We're going to open a canvas together. So if everybody wants to follow me on this one. So we're going to open a canvas. You can either specify the size, or you can leave it blank. That's totally fine too. But I'm going to say, let's say it's going to be an 8x8. We're going to call PLT because we imported that, right, up top. Imported matplotlib.pyplot as PLT, so I'm using it. And why don't we just do a really simple scatter plot? And it's going to be really ugly, but it's going to be fine. It's going to look great. So we're going to take wine, and let's do the same thing. Let's take wine alcohol, and we're going to put that on the X. And we're going to do wine and quality. We're going to put that on the Y. We're not going to do anything else. The only thing we're going to do is, it actually should run, but just to make sure, we're going to run plt.show, just to really make sure our plot shows up at the end. Okay. It's like not the prettiest plot in the world, but we got something. So are we able to recreate that? Okay. So we can, let's maybe even just start even simpler. Let's just do same thing. I'm going to get rid of the scatter though, and I just want to plot out all of the alcohol quality scores. So we'll do wine.quality. We're going to put that in plt.hist for histogram. And why don't you guys specify how many bins? Remember we got like 7,000 points. Maybe we'll do 50 bins. Doesn't really matter because I put quality. I probably should have put alcohol, because it's still nominal. Sam, get it together. Let's try alcohol instead. Okay, slightly better, 50 bins, right? It looks more like a histogram. Maybe not. And if we want to, we can even make it a little bit easier for everybody to see, right? So this line up top changes how big the canvas is going to be, and plt.hist just makes a run-of-the-mill histogram for us. So maybe instead we could also do, oops, sorry, I deleted that line. Does that make sense to everybody? Okay. Do we want to do because we got about 10 minutes left. Do we want to do some more visualization, or do we want to maybe quickly move on and do some basic work with the data frame itself? What would people like to see?
What about this plot you asked us to use?
Mhm,
Like,
sure.
How would you just?
So let's take a look at the docstring there. So displot is actually very similar to the histogram in that, in fact, we can actually pull them up. So before we even look at displot, let's look at plt.hist, and let's just see what all the commands are. And make liberal use of command .question mark, right? So we put in the data, it's a one-dimensional array in X, the number of bins, we can specify the range of the values, we can say whether that's a normed histogram, so whether or not everything sums up to 1 or not, we can do weights. But really the main things that we really need to focus on are just these two, right? We just need to focus on the data we're putting in and the number of bins we want to use to draw the histogram. Displot is remarkably similar actually. A here is just the array, and bins is the number of bins. And then we can do other things. We can ask, do we actually want to draw a histogram? Or do we want to draw a KDE, which is a kernel density estimation. So can we draw basically a line over the histogram? And rug puts all the points in there. So let's maybe try a few of these. So I'm going to take alcohol again, right? So we're going to take the alcohol variable, and I'm not going to do anything else. I'm just going to use all the default values, and that plots out. If it's not running for you, maybe the issue is that there's a software issue. We can also debug that afterwards. But let's try a few other things. So what happens if we set hist to false? Okay, so all the bars went away, so we only get the kernel density estimation, and we only get the line up top. So all I did there, I just set hist to false, and KDE is still set to true. But maybe we'll set rug to true as well. Rug's not normally true. What do we get? It's going to take a second because it's drawing now 7,000 lines at the bottom. Ugh. This is the waiting game. This is why I have a desktop at home. I have no patience for you, rug. Okay. Normally, what you would get is something like this. If that had an example, that'd be great. So normally you get something like this. It's just going to look really cluttered because there's 7,000 of them. But normally, when you specify rug is equal to true, you get a bunch of ticks at the bottom, which let you know where your data point actually fell. So that's not going to happen in this millennia. So we're going to let that one go. But we can also, for example, switch KDE to false and hist back to true. And in doing so, we just get the histogram. We don't get the line estimation. That makes sense to everybody, right? And we can do some other things too, right? We can set colors equal to R for red if I put it in a string. And okay, so we're able to change the color on that, which is nice. Maybe we don't want it to be dark and mysterious anymore. Maybe we want it to be light and carefree. So we'll do set style, and we'll do maybe set styles to white grid. So we get a white background and black grid lines. And if we set style back to white, then we get no grid lines. And then we just have this very minimalist histogram. So those are some of the things we could very quickly do for histograms with this plot. You can change color, you can change the fit, you can change all sorts of different things in here. Is that a better example for this plot? Other ones could we take? Another very quick one that we can do with our last few minutes, maybe let's do LM plot. LM plot basically tries to do a scatter plot, and then it tries to basically just draw linear regression through it. So let's look at that docstring real fast. It looks annoying. But all we have to really do is just pay attention to these first three, and we should be good to go, right? X, so what do we want on the X? Y, what do we want on the Y-axis? Data, give it a data frame. Q, if we want to split it by anything. Let's just start with those four. So let's say on the X again, I want alcohol. On the Y again, I want quality. And even though it's a nominal variable, it's not continuous, but we'll let that go. Data is going to be equal to wine. And I want to split it on the color of the wine. And I'm not going to specify anything else. I'm just going to let that one go. And yeah, I'll just let that one go. Okay, so it looks a little bit like a monstrosity because we have a whole bunch of points on top of each other, which is to be expected. But the core of it worked, right? We did get 2 trend lines through it, so that's a start in the right direction. How can we fix all these dots? Well, let's go back to the docstring. That's displot, Sam. Keep up with yourself. There should be, and in fact there is, an option for us to specify bins so that we can actually bin all of those dots to make them go away. So we want to bin along actually let's reverse this. Let's actually put quality on the X and alcohol on the Y real fast, just to make it simple. And I'm going to set X bins equal to the unique values that we have of our quality. So X bins is going to set equal to wine.quality.unique. Those are going to be my bins. I want to put all those points into those unique bins. And that looks remarkably better. All those points just disappeared because instead of letting them flutter around and pollute our graph, we put them and we bin them together with just 5 total calls to lmplot. And if you thought, well, Sam, that doesn't really look linear to me, maybe we could try doing something else. So lmplot also lets you fit higher order polynomials. Or at least memory serves it does. Ooh boy, somewhere in there. Let's see if it does. If not, it's regplot. But let's say order is equal to 2. Yeah, it does. Okay, cool. So now we're able to fit a polynomial trend line through there. Doesn't really look like it's a much better fit, but it's an option, right? So these docstrings are really, really complicated, but to start out, the main thing I always recommend when you're trying to parse this stuff, ignore everything but the first 3 or 4 when you're starting out. And don't worry about trying to make everything really custom. Don't worry about any of that. Just get something basic onto the screen, right? Start out with the first 4 because almost in general, Seaborn is always going to basically be looking for the same 3 things always. What do you want on the X? What do you want on the Y? And give me a data frame. And if you can give it those 3 things, 9 times out of 10, you can get a basic plot out. And if some of the gallery stuff looks a little bit too complicated, there's also really good documentation on the tutorials where they'll show you how to fit everything for univariate distributions and bivariate distributions and linear relationships and categorical data. So there's tons and tons and tons of documentation to go through. So take it slow. Don't try to make the world's most beautiful plot all at once. Make a really ugly plot, but get something on the screen first. That's actually 90% of my plots as is anyways. So be better than Sam very quickly. So that brings us to 9. I'm happy to keep going. I think it's been a long day probably for most of you. So I'm happy to stick around if people have questions, if you want to try out more exercises. Take a